Today we'll be looking at Chapter 6, which discusses structural analysis. So Section 6.1 of Chapter 6 talks about simple trusses. So trusses are commonly used to support roofs and a variety of structures, like cranes and frames of aircraft and of space stations. How can you determine the forces in a truss, or the members of the forces of a truss? And how do you select their sizes? For a given load, how can you design the truss's geometry to minimize costs? These are some of the questions that pop up when you begin thinking about trusses. So what is a truss? A truss is a structure composed of slender members joined together at their endpoints. If a truss, along with imposed load, lies in a single plane, as shows on the top right, then it is a planar truss. This can often be found in roofs. A simple truss is a planar truss which begins with a triangular element and can be expanded by adding two members and a joint. For these trusses, the number of members, m, and the numbers of joints, j, are related by this equation here, where m equals 2j minus 3. So on the top right, we see a simple truss, which is just that triangle we see. And then we see that you can expand on a simple truss to create more trusses by just adding members to it. So our analysis and design assumptions when we're analyzing truss. When designing the members and joints of a truss, first it is necessary to determine the forces in each truss member. This is called the force analysis for the truss. When doing this, two assumptions are made. All loads are applied at the joints, and the members are joined together by a smooth pin. So it's important to focus on the point that all loads are applied at the joints. The weight of the truss members is often neglected as the weight is usually small as compared to forces supported by the members. The members are joined together by smooth pins. This assumption is satisfied for most practical cases. If you imagine or ever see a truss, you always see them going to a singular point, which is normally a pin. When these two assumptions for trusses come together, the members act in a two-force member. They are loaded either in tension or compression. Often compression members are made thicker to prevent buckling. So in the picture in the left, we see tension is this pulling of the member, and compression is kind of pushing it together, compressing it. So the reason why compressive members often are built thicker is to prevent buckling, which if you can imagine, if you take some type of, imagine as just a string of a noodle. If you compress it, you can imagine it snapping. And to prevent it from snapping or buckling, you normally make members that are feeling compression thicker. Method of joints. To solve for the forces in the truss members, the equilibrium of a joint, which is a pin, is considered. All members are acting at the point are shown in a free body diagram. This includes all external forces, including support reactions, as well as forces acting in the members. Equations of equilibrium, which is the sum of forces in x and the sum of forces in y equals 0, are used to solve unknown forces acting at the joints. So here we see an example of an unknown force acting at the joint B, at the point B here, where you can see that you could either determine it as compression or tension. Just for analysis, when you're looking at the method of joints, is to draw a free body diagram, the entire truss, and to determine the support reactions. When you're drawing the free body diagram with one or two unknowns, assume that all the unknown members are acting in tension, which is pulling on the pin. But you can determine by inspection that the forces are compression loads if they're being compressed. So always assume that's in tension. But if you can tell that it's being compressed, then you can label it as a compression force. Apply the scalar equations of equilibrium. We know these equilibrium equations. And then you want to repeat the drawing of the joint free body diagram and the equilibrium equations for each and every joint that is in the system until you solve for all the unknown joints or all the unknown members of the system. Let's take a look at our first example. So this example is asking us to determine the force in each member of the truss and then indicate whether the member is in tension or compression. So we have this simple truss where we see that at the joint B, there's 500 newtons being pulled in the right direction. So the first step is to draw a free body diagram, which is going to be for each individual joint of interest, and then we're going to solve the equations of equilibrium for each joint. So for joint B, we see that we have that 500 newtons, and then we have the angle between the two forces. Here they show that the force from FB is compressing onto that joint, and then the FBA is the tension. So solving this, we find that FBC gives you 707 compression, and FBA is 500 newtons in tension. Repeat the same thing for joint C. We see that at joint C, FCA is 500 newtons in tension, and that the support acting in the vertical direction is 500 newtons. And then at joint A, where we find our last equations of equilibrium and free body diagram, we already have the values of the joints at FBA and FCA from our previous joints. So we have the values of the members, and then the final support forces that we can find here is that A of X equals 500 newtons and A of Y equals 500 newtons. So what's important to keep in mind here is that what you want to do is draw a free body diagram into each of the joints until you find all the unknown forces that are acting in the system. Point 3 introduces the concept of zero force members. So when you're doing truss analysis, some of the members are labeled as zero force members. These are members that support no loading but are used to increase stability for truss during construction. So what they are normally used, even though they have no loading on them, they are often used just for when you're doing construction or if there's a change in the actual loading itself that's happening on the truss so that it could sort of balance it out. But when doing analysis, you'll find that that member is equal to 0 for in terms of force. So these zero force members are found if a joint has only two non-collinear members and there is no external load or support reaction at that joint. Then those two members are zero force members. So in this example, the two zero force members would be the joints A and D, which would mean that if we had just a truss that looked like this, where there was neither of those joints and the members connected to it, it would be the same or same overall, because those point DC and the members of DC, ED, AB, AF all equal 0. This makes sense, right? Because at point A, the reason why the two members are 0 is because we see that member AB, the force can only act in the X direction, and then for that member FA, the force can only act in the Y direction. So the two members must hold 0 force because there is no counter force to keep it in equilibrium. Another way we can find a 0 force member is if the three members from the truss joint are collinear and there is no external load or reaction on the joint. And then there's a third non-collinear member. This would be the zero force member. So in this case, joints D and C, where we have the member from A to D and the member from A to C. This would give us a truss that looks like this, because the reason why the member AD has zero force is because we see that the force along the axis ED and DC, those are exactly collinear, and then there's no other force to balance out that force AD. Take a look at our second example. So they asked us to use the method of joints to determine all zero force members of the Fink roof truss. Assume that all the joints are pin connected. Take a look at first the joint G. We see that here the member FGC is 0 because the two members FGF and FGH are collinear, and there's no other external force or anything else balancing with the FGC, so that must mean that that joint FGC is 0. The next joint D, similar to FGC because it's perpendicular to two collinear forces with no external load on it, that this force also must be 0 for this member. And taking a look at joint F, if we consider that from the previous statement that joint FD is a 0 force member, that means FC must also be 0, right? Because we're saying that FD is no force, and there's nothing else I can balance out with FC, which must mean that FC is also 0. 6.4 discusses the method of sections. So if we have a really large truss or a large tower, for example here, the method of joints would be hard to use because then that would require us to analyze a lot of different joints instead of our focus of interest. So for example, for this tower, if we just wanted to figure out what the forces were for the middle of the tower, the method of joints would require us to find joints all over the entire truss. So the other way to determine what the forces are in the members of a certain section is by sectioning off the members. So in the method of sections, a truss is divided into two parts by taking an imaginary cut, as we see in the image above, through the truss. Since the truss members are subjected to only tensile and compressive forces along the length, the internal forces at the cut members are also either tensile or compressive. So they will have the same force equal sides. So if you see the right image there, we see that if you tug on a member, you see the tension pulling it from the top and the bottom are equal. But if you were to split that member in half, it still would be equivalent for the amount of tension between them pulling it or keeping it together, the tension that's keeping the member together. So it's saying that it's uniform throughout, and this comes from the equilibrium principle from Newton's third law. So the steps for analysis for a method of sections is to decide how you need to cut the truss. This is going to be based off of which section you find as interest, or which section has the least total number of unknowns. You often want to keep it at 3 unknowns. The more you get past that, the more complicated the problem gets. So 3 unknowns is usually what you try to stay at. Then you decide which side of the truss to cut, which one will be easier for you to work on. And if it's required, determine any of the necessary support reactions by drawing the free body diagram of the entire truss and applying equations of equilibrium. So sometimes we need to do what we did previously, where you find the forces of the entire truss, right, or the supports. So in this example, you'd need to find what dy, dx, and ex are for the support before you try to find the individual members. Fourth step is to draw a free body diagram. Select the part of the truss And then you need to indicate the unknown forces at the cut member. So you need to label what your forces are that you're looking at. And then lastly, you apply the scalar equations of equilibrium for this cut section, and then you determine what your unknown member forces are. Taking a look at example 3, it asks us to determine the members GE, GC, and BC, and indicate whether the members are in tension or compression. So first, we're going to need to find the equation of equilibrium for the supports. So we need to determine what the dy, ax, and ay are in this case. See that ax equals 400, dy equals 900, and ay is 300 based off of the equations of equilibrium. We then decide which section we're going to cut or look at. Here we're going to look at the left side. We're going to cut right between those three forces that are of interest. And then the equations of equilibrium here are for the force of GC, you can use the forces acting in the y direction. For the force of GE, you can use the moment from that point C. It shows it as imaginary, but if we look at the whole truss, that point C is the same. It's the same joint that we saw before we did the cut. And then for BC, you can do a moment around the joint G. And solving for each of these equations of equilibrium, you get the following forces where the force in GE is 800 newtons in compression, and the other two forces we see that are in tension. Section 6.5 discusses space trusses. So a space truss consists of members joined together at their ends to form a stable three-dimensional structure. So this is kind of looking at trusses, but this time it's in 3D version. The simplest form for this, instead of a triangle, is a tetrahedron, and it looks like the image on the right. The normal assumptions for this is that the members of the space truss can be treated as two force members that give external loading, and that the given external loading is applied at the joints, and the joints consist of ball and sockets instead of what we saw before, which were just pins. Look at this example for the space truss. It asks us to determine the forces acting on the members of the space truss and then indicate whether they're in tension or compression. So here we have a free body diagram for joints A, joint B. It's very similar to what we were seeing before, except this time we're doing it in 3 dimensions. First, you need to use your equations of equilibrium to just first figure out what the forces look like in Cartesian. And then here we have the equations of equilibrium for joint A, where the forces all add up to 0 because the joint A is as if as a particle, and the equilibrium for that means that all the forces must add up to 0. So when you're looking at the equations of equilibrium for joint A, when you write it all out, you end up getting that the force in the member AC and AE are equal to 0, and then we have that force in AB is in tension at 4 kilonewtons. And then we can solve for joint B, where we find that the member BE is 0, the member CB is 5.65 kilonewtons of compression, and the member BD is 2 kilonewtons in tension. The last section of this chapter is section 6.6, which discusses frames and machines. So frames are commonly used to support various external loads, and to be able to design a frame, you need to determine the forces at the joints and supports. So frames are sort of different from trusses in the fact that instead of the force being applied at the joint, it's applied on a member, or it could be in the middle or at a different point in the member. Machines, there are usually a variety of applications. We see above that these are two different examples of machines. The question is how um, are machines different from trusses? Well, here we're saying that you're applying a force to create a force or change in another location. Trusses are usually used as just a support to keep things from moving. How can you determine the loads at the joints and supports? This is a question that we're going to be solving in this section, and then these forces and moments are required when designing machines and members. So the reason why machines are important is because you need to know what forces and moments are occurring in which areas to know how to create a certain machine or how much load it can handle when you're trying to utilize a machine. So the left we see a frame, and the right we see an example of machine. So frames and machines are two common types of structures that have at least one multi-force member, which if you recall, trusses only have two force members, right? So two force members is just that tension and compression, but what makes it multi-force here is that there's not just tension and compression, there might be another force that's acting directly on the member. The frames are generally stationary and they support external loads, while machines contain moving parts and are designed to alter and um, affect forces. Step for analysis. So first, you want to draw a free body diagram of the frame or machine and its members as necessary. You want to identify any of the two force members. Then you want to note that the forces on the contacting forces, this is usually between the pin and the member. So an example on the bottom left is that force 2000 that's pointed downward. That is between two pins for B and C. That would be the external contact force. And then for a joint with more than two members or external force, it is advisable to draw another free body diagram for that exact point. Step two is to develop a strategy to apply the equations of equilibrium. This can be very different depending on the types of equations, the questions you're looking at. Depends on if you're looking at a frame or machine. Depends on if it's like a pulley, members, or if it's in some other type of system. Problems are going to be challenging since there's usually a lot of different unknowns, but by practicing more and more problems, you can figure out different strategies to simplify the problems. So let's take look at this example 5. They asked us to determine the tension in the cables and also the force P required to support 600 Newton force using frictionless cables shown below. So we see that there's a pin A, B, and C. So these are three different pulleys, and we want to find the tension in the cables, and we also want to find that force P that's being pulled. So first we draw the free body diagrams. We see that for the pulley at point C, we see that we have the two P's pulling from one side to another because we know that for a pulley the tensions are the same on each side. We see that R tension representing that string that's holding the pulleys up. And we see that other T, which is between that point C and point B. And we see for this pulley B, we see that the same P value, because if you notice, throughout the entire pulley, all of it is using the same string, right? The same pull, right? We see that T that's holding the point B up, and then we see that for pulley A, we see that same string P holding the hook up, and then we see that 600 newtons coming down. So equations of equilibrium, we can solve for each pulley A, B, and C. For A, this is what the equation of equilibrium will look like. It's 3P minus 600 newtons. For B, it's T minus 2P. And for pulley C, it's R minus 2P minus T. Then when we solve the problem, we find that P equals 200 newtons, T equals 400 newtons, and R equals 800 newtons. Let's take a look at our last example. So the problem asks us to look at this compound beam, which is connected by a pin connecting at point B, to determine the components of reaction and its support, and then to neglect its weight and thickness. So the free body diagram for this will look like this example. You see how we break it up into two different free body diagrams for each of the members, each of the sections, right? So at that point B, since it's a pin, you only have that Bx and By forces since it's allowed to rotate around, since it is a pin, not a stuck support. So we can first solve for segment BC, where we have the following equations of equilibrium, right? The reason why we're solving this section first is because it has less unknowns than the other section. We find that this section BC has B of x equals 0, C of y equals 4 kilonewtons, and B of y equals 4 kilonewtons. And then we could look at the other segment, AB. We have the following equations of equilibrium, but from the previous problem, or the previous section, we have our unknown, some of the unknowns already solved for, which are Bx, By, right? So we could use those in solving this equation. And we find A of x equals 6 kilonewtons. The moment around A is 32 kilonewtons meter, and then A of y is 12 kilonewtons. So the important thing to keep in mind here is just making sure you're able to section off into different free body diagrams to be able to solve for the overall forces, and making sure you're showing the forces canceling out correctly. And that is chapter 6. Let me know if you have any questions.